And you'll see you'll get gamma squared times E naught times this term. And then here, minus gamma squared times the E field will be 0. It will work. So this is the general form of the solution. This term right here is for positive Z propagation, and this term is for minus Z propagation. What I mean is, when we go to the time domain, we'll find out that this term right here has to do with a wave propagating in the positive Z direction. And this one has to do with a wave propagating in the negative Z direction. Y'all follow me on that, class? I'll show you how to get that in a little bit, but for now, you just accept it. So now we'll put it back to the time domain. We'll do it over here. Get rid of this.
I can't remember what Greek letter is that.
Gamma.
That's gamma. Okay.
And so now we take a look at this. I'm going to take a look at this equation right here. And I note that gamma is equal to alpha plus j beta. And I want to go to the time domain based on what I've told you before in the phases. Then I say that E in the time domain, now this is the observable domain, would be the real part of E to the j omega t times that E field. So it's times E naught plus E to the minus alpha z, E to the minus j beta z, plus E naught minus E to the plus gamma z, E to the plus j beta z. And it would be in the AX direction. So, I'm going to stop. I don't mean to give you, just a lot of redundant information, but I wanted to write this down. Remember what we did with the voltage before current before to bring it to the time domain? Y'all remember that? This is exactly what we're doing here. That's phasor. Now we're bringing it to the time domain. You'll notice I have E to the j omega t times these terms, right? I'm going to combine them once to do this. I don't usually spend much time on this. So now I have the real part of E naught plus E to the minus alpha z, and then I have E to the j quantity omega t minus beta z here, plus E naught minus E to the alpha z, E to the plus j omega t plus beta z, and it is in the AX direction. I've just combined terms to show you. Just trying to sort of concatenate this thing down. Oh, and this, by the way, that negative is on the E field right there. I'm trying to just show you that has to do with the magnitude of the negative travel wave. Now when I take the real part of this, I know when I expand this term, let's see, the E to the minus alpha z is strict real. When I expand this term, I get cosine of omega t minus beta z plus j sine of omega t minus beta z, right? The real part is just the cosine. Do y'all follow me? So when I bring it into the time domain, what I actually get is this. I get E naught plus E to the minus alpha z, and I get cosine of omega t minus beta z, and then I get plus E naught minus E to the alpha z times cosine of omega t plus beta z, and these are all in the AX direction. Now that is my E field. This term is propagating the plus Z direction. This term is propagating the minus Z direction. If you don't believe me, you can use MATLAB or your favorite piece of software, and literally you can let Z be, or you can actually use this equation and go for from 0 to maybe 20 meters on the Z-axis, and start at t equals 0, just find a solution, forget that one for now, just use this part, and graph the thing out, then increment times a small amount, and you'll see literally the wave traveling in the positive z direction. And likewise, if you do that for this equation, you'll see it traveling in the negative z direction. All right, it's really something I might even give you a piece of homework has to do with that. But that's something that comes out of this. Remember, with plane wave propagation, that's the E field in the time domain. Okay, so far? You remember, how many remember seeing that? I know you guys did, because I talked to you. Did you guys see it in your, no? You did? Who did you have for your night one?
Bashir.
Adele Bashir probably would do it. Anybody have Wentworth?
I do, but it was a year ago, so I don't remember.
All right, anyway, so this is propagation of the E field. Now, likewise, the H field, when we're talking about any kind of propagating electromagnetic phenomena, the E field and H field are linked. If you know one, you know the other. They're linked. So, how do you get the H field? I'm gonna leave that there for now. We come back over here. You don't have to write this down, you can just appreciate it if you want. So for the H field, remember what I started with was curl of H is equal to sigma E or sigma plus J omega epsilon times E. And I had curl of E is equal to minus J omega mu times H. I'm starting right here. Y'all remember that? You don't have to write it down, but just appreciate it. You remember how I got there, right? I start with the fundamental equations. I use the coupling. J is sigma E. D is epsilon E, and H, or really B is mu H, and then I got it down to here by drawing the phasor domain. Now I'm going to get one equation for just H. And I do that by taking a double curl of the H equation. That's equal to sigma plus J omega epsilon times curl of E, right? Y'all follow me on that? What's my next step? Remember from the past, anyway. Remember, I want one equation, one unknown. Now, this time I want it in H. What am I going to do to that equation to get rid of that curl of E?
Plug in
That, right? Sure. I'm going to say that this curl of H now is actually gradient divergence of H minus del squared of H, right, is equal to sigma plus J omega epsilon. And then the curl of E will be replaced with J omega mu times H. So now I've used this second equation to plug in for curl of E, and I get this. Do y'all follow me? Now I'm going to sort of, I know that that's gamma squared right there. So I have minus gamma squared H over here. And I come down to here on this side. And I'm going to do something, I'm going to ask you this. If divergence of D is rho V, and we assume that's zero, right? The charge-free region. What is the divergence of B going to be and why? If that has to do with electric charge density, right, and we assumed it's zero, what does the divergence of B have to do with? Think about it. Magnetic charge. Do you follow me? Is there such thing as magnetic charge? Monopoles? Absolutely not. Well, yes and no. Absolutely not in the macroscopic world we live in. There is no such thing as a single piece of positive magnetic charge. It always occurs in dipoles. Did you all know this? All right, real important to know that. Now, if you go to the super colliders, superconducting systems they have in Europe, where they do atom smashing, they take things and they whip them around at enormous speeds and then collide them, and they look at a gas, one of these gas bubble chambers in the aftermath of that collision. They will find that there is magnetic charge that exists for, I don't know, picoseconds, femtoseconds, but an observable length of time, and they only exist at the extremes for very short periods of time. So when they have enormous temperatures, and only for very short pieces of time. So there technically is a magnetic monopole. It's just, its existence is so short-lived. We don't even talk about it. It doesn't affect us. We assume it's zero. So we assume this is zero. That also means divergence of H is 0 as well. All right? The divergence of H is 0, it gets rid of this term. You all follow me? So now I get back to this. I get del squared of H here is equal to, or del squared of H minus gamma squared of H is 0. And that is identical in form and fashion to the field equation we had for the E field. Y'all follow me? Exact form. So the E field was assumed, what? The E field was assumed to be in the X direction, right? Now, if you come over here, I wish I had a, it's in the physics building, I have 3 boards. Did y'all have this here? You know where they have 3 chalkboards you can push up and down? I don't know why they don't do that in engineering. I mean,
half the time my professors couldn't even reach the 3rd one, so it was always.
these are chords. I mean, if you ever look at the MIT website, or go to MIT or probably Harvard too, go look at the physics lectures from some of the older professors. They use these big giant chunks of chalk. They'll have pink and yellow and white and stuff like this. They'll have these chalkboards, and they'll be pulling these boards up and down and writing these extremely long equations, and just leave it up there for reference to always point to. I've always been impressed by those boards. I wish I had. Because it saves all the erasing. All right, so now we know that the E field, we're going to do this. We're going to take a look at the E field as just E naught plus e to the minus gamma z ax. We're only going to look at the positive traveling portion of the E field for now. We're going to examine some things. So when I have this, I know there's a relationship between E and H. I know that curl of E is actually equal to minus j omega mu times H, right? In the phasor domain. So now I'm going to do the curl of E. In the back of your book, on the back cover, does anybody have your book here? I always encourage people to bring your books to class. You don't have to, but it helps because I'll tell you where to write stuff down. You'll have the vector identities for curl in the 3 coordinate systems: Cartesian, cylindrical, spherical, divergence, gradient, and Laplacian. And Whitworth's book has this in the back as a courtesy. Most EMAG texts do. Something that I'll have this very easily available. Well, when I do the curl I'm going to do it in Cartesian coordinates because that's the one we're using. When you take a look at curl of E, really what you're talking about, I like doing it in terms of a determinant. You put down AX, AY, AZ, then you put down the derivatives, ddx, ddy, ddz, and then you put down the field quantities, EX, EY, EZ, and you execute the determinant. Y'all remember doing these things in linear algebra?
Yeah.
Okay. Now, I like doing it this way. I know the only field quantity I have is EX, correct? I don't have any EY or EZ, so I get rid of this and put zeros in. Now when I look at this curl, well, I take what? I go down the diagonal, I start at AY ddz of EX, so I have AY ddz of EX minus, and then going this way, minus ddy of EX AZ. That would be the curl. Do y'all agree with me? I'm just doing, y'all know how to do determinants? How many know how to do determinants? Okay, I want to, you know, your response isn't required, but it's nice to know. So, if I take a look at this, what's the derivative of EX with respect to Y? Look at the functional form of EX. Is there any function of Y there? No, right, so what's the derivative of something that's not a function of y with respect to y? Zero, yes. So this term doesn't exist. So we have that term. Now, we come over here, and I'm gonna say curl of E is really AY, right? And it's d dz of that quantity, E naught plus times e to the minus gamma z. And that's equal to minus j omega mu h. Now just take a look at this for a second. I'm showing you how to get the h field, if I want to, directly from here. You take a look at this, and I take a derivative of this with respect to z, brings out a minus gamma. So I get the ay direction, I get minus gamma, right? And I have E naught plus, I have e to the minus gamma z, and then I divide by minus j omega mu, and I have my h field. I'm going to clean it up in a second. Do you all see what I've done here? I've divided by minus j omega mu, right? And I've simply executed the derivative with respect to z. It just brings out the minus gamma. You all follow me? Everybody? All right, now, I'm going to get rid of that minus sign. It occurs in top and bottom. You all follow me? So I'm going to get rid of the minus sign. Now after that, I can see one thing. I have a field quantity where I can take the j from downstairs. Actually, no, I'm going to leave it like that. But I can see something. I have an AY orientation. I have that as a magnitude propagating in the minus gamma z direction. So what I can actually say is h is equal to some h naught, plus direction, e to the minus gamma z I've already told you that would be the form of the solution. Do y'all remember this? It's in the AY direction, of course, the orientation. And now what I'm going to do is get the ratio. Let me try to clean this up a little. So I have E naught plus over H naught plus is equal to J omega mu over gamma, and the minus gamma stuff. And this is called the intrinsic impedance. I better put it over here. This, what I'm showing you here, this is the intrinsic impedance. Of the actual region. And I'll clean it up a little more. Let me do it right here so you can see it better. So I have eta is equal to the magnitude of E naught plus over H naught plus. Well, it's the ratio of these two, and it's equal to square root of J omega mu over sigma plus J omega epsilon. Now, I want to just mention something. Here, if you look at this, you see how this is J omega, this is J omega to the 1/2 power? Can y'all follow me on that? Well, if you go ahead and square that, then you can put the square root operator there, and then you'll see J omega mu will appear there, and this J omega mu will go away, and you'll be left with this. And this is the intrinsic impedance in the region. does that really mean? Well, you remember how when you had transmission line theory, you learned something about the characteristic impedance of the transmission line, right? That was the ratio of V naught to I naught. Do y'all remember that class? It didn't have anything to do with the DC resistance or anything like that. It had to do with propagation. And this is similar. The intrinsic impedance of the region, if we talk about what it is for free space, eta naught is going to be the free space intrinsic impedance. Now, if it's free space, I would have J omega mu. Mu still exists, but what's sigma in free space? We're in a vacuum. Anyway. Take a guess. 0, right? There's no current possibly conducted in a vacuum. Do you all follow me? If there's no charge density, no current can flow. It's really just a simple fact. So if it's free space or a vacuum, it's assumed to be 0, and that would be divided by J omega epsilon, right? Now you all see the J omegas are canceled. In other words, sigma will not exist in a vacuum or in free space. And that means it's simply square root of mu naught or mu naught over epsilon naught. And this is as a very, if we could put down the values of mu and epsilon, but it is 120 pi ohms or about 377 ohms. So if we're talking about air right in our room here, or the atmosphere, lower atmosphere, the ratio of E to H for a propagating wave is about 377 ohms. It means if you know E field, you know the H field in terms of its magnitude. Do you all follow me? Now something else I didn't get to, I'm going to spend a lot of time talking about some of these things, is whenever you have an electromagnetic field propagating, a plane wave, we're a long way from radio stations. Say we're talking about we build FM's antennas on top of Haley, I think. So we're fair ways from them. If we could look at the electromagnetic field propagating, that's a big if, and we could freeze time, we'd see the electric field oriented this way. I'm assuming it's vertically polarized. The magnetic field will be orthogonal to it. So if the E field's in this way for a propagating wave, the H field has to be orthogonal, and both of them are orthogonal to the direction of propagation. Now, if they were propagating this way, you have E field this way, H field this way. Do you all follow me? And whenever you have E and H field propagation, if you take your right hand, assuming you have one, and put your index finger in the direction of the E field, and then just turn the door open into the H field, your thumb will point in the direction of propagation. How many knew that, by the way? I know you better have done this. Yeah, and that's something to know. We'll get to that later with power, but E cross H is always the direction of propagation. And now, now that I'm getting places, I'm trying to make sure I don't want to spend too much time just doing random theory and things like this. I want to do one other thing too, two other things, hopefully, we can propagate field. You've heard, you know, if in general you talk about velocity or wavelength, these are important things. They're fundamental too. When we talk about phase velocity, one thing we assume is we have a wave that's propagating at a constant frequency. And remember, I'm going to go to the time domain now. If I have an E field, this will only be a positive moving, or an E field moving in the positive Z direction. Will be some E naught plus times. I'm going to assume alpha is 0 for this one, times cosine of omega t minus beta z ax. This would be a legitimate wave propagating in a lossless medium. Right? Now, if you want the phase velocity, the key is knowing what they mean by phase. It's the argument here. You all agree cosine of something has to be the cosine of an angle, right? That angle would be the phase. So how fast is that angle moving? Well, that angle is omega t minus beta z. That would be the phase or the argument of the cosine at any point in space-time. Correct, class? The way you always get velocity is taking a derivative of the position quantities. So if I take a derivative of the phase here, now I'm taking a look at, I don't want this angle to move, so the quantity omega t minus beta z, I want to say that is locked. Do you follow me? Because I'm going to take a derivative of this and set it equal to 0. Now the phase doesn't change. Do you follow me? And that would be equal to what? Omega minus beta times dz dt. Just try to understand. What I'm really saying is I want to find out how fast the crest of that wave, if you will, is moving. I'm calling the phase like, if it was a cosine argument, cosine is 0. I want this to be 0 always, all right? I want to see how fast that cosine of 0 is moving, the omega t minus beta z. So I take a derivative of this argument with respect to t and set it equal to 0, and I get omega minus beta times dz dt. Now, anytime when you've had physics, you see dx dt, what do you think of in physics? Velocity, right? Don't you?
Yeah.
Right? dx dt, dy dt, velocity, right? dz dt, velocity in the z direction. The rate of change of the position with respect to time is a velocity. So that means the phase velocity is dz dt, and that's equal to what? Omega over beta. That's always true. That's phase velocity. Happens to be the velocity of propagation too for plane waves. Oh, that's the phase velocity. How do you get wavelength? We have to be a constant frequency, right? But how do you get wavelength? Y'all know the symbol wavelength? It means what? It's the distance over which a wave repeats itself, right? When I'm talking about wavelength. So when I talk about wavelength, I take a look at that quantity. E is equal to E naught plus times cosine of omega t minus beta z. I want wavelength on this one. So here's what I'm going to do. I'm going to get rid of the time variable. I'm going to assume t is 0. So I get rid of that. Don't worry about that. Do y'all realize that cosine of minus beta z is equal to cosine of beta z because it's an even function? Like cosine of x is equal to cosine of minus x. Do y'all know that? It means it's an even function. So if I take a look at this, I might as well just make it cosine of beta z. Now, if I take a look at this, the cosine of beta z would look like this versus z. This would be the E field in this axis, okay? And that's not drawn very well, but I hope you can appreciate what I'm trying to do. I'm trying to show you a sinusoidal waveform, cosinusoidal wave. The wavelength is from here to here, right? That would be the distance over which the wave repeats itself. Do you all agree with that? How do you get that? What is that always equal to in terms of degrees? How many degrees is a wavelength? Think of basic physics. These circuits. 360 degrees. Y'all, that's a complete wave, right? When you go 360 degrees. Well, that means that here, when I'm at the origin, it's cosine of 0. Here, when I'm one wavelength away, its beta wavelength is equal to 2 pi. Do you all follow me? 2 pi radians. So I find out that wavelength, or really beta times the wavelength is 2 pi, or the wavelength is simply 2 pi over beta. And that's fundamental, that's always true. That's always phase velocity, that's always wavelength. Okay. Now, and where I'm going to now is on page 327 of the text. Now, what I call these shortcuts, tricks, things that make life easy. If we're talking only about plane wave propagation, and we're in the phasor domain, if I have E, I have H, and if I have H, I have E, and here's how you get them. And this is a little trick. All right, first we talk about A sub P is a unit vector in direction of propagation. Unit vector has a magnitude of 1. Direction is the direction the waves move. So if I wanted the H field and I had the E field, this would be in the phasor domain. I would take 1 over the intrinsic impedance, that unit vector AP crossed in to the E field. And if I had the H field and I wanted the E field, it would be minus eta times the unit vector in the direction of propagation crossed into the H field. And these are on page 327. But they make life easy, because if you have one, you need the other, you can do this. Now something I'm going to tell you though, that eta right there can be complex, which means you would have a magnitude there and you'd have to put a phase angle, and you can take the phase angle on top. So there is a little trickiness to this. So I'm going to end with this. I talked about phase velocity, right? Now we're going to take a look at what phase velocity is in free space. And here it's in free space. Call it a vacuum. That's fine. Well, I can see phase velocity is omega over beta, right? So now I've got to get beta. And I look, and I remember the way I get beta is from gamma. And gamma is equal to the square root of J omega mu times sigma plus J omega epsilon, right? I'm just restating what I did earlier. I know it's a lot coming at you, so I'm with you on that. But you all remember that at least routine, that I put that up there before? Okay, now we're in free space. What's the value of sigma?
0.
0. Go and get that thing out of there. Now when you look at this, you have gamma simply equal to J beta, sigma 0 equal to J omega mu, or J omega times square root of mu epsilon. Do y'all follow me on that? Because you've got 2 J omegas on the square root side, so you bring out a J omega, then you have the square root of mu times epsilon. Do y'all follow me? Can you all see it? Can you see it over there?
Yeah.
All right. That means beta is equal to omega times square root, and now we're assuming free space, so it's mu naught epsilon naught. So now I come back over here and I find the phase velocity in free space is omega over beta. And guess what? That's 1 over the square root of mu naught epsilon naught. How many know what 1 over the square root of mu naught epsilon naught represents?
What's the speed of light?
Speed of light in a vacuum. In a vacuum, exactly. So the phase velocity in free space is usually labeled c, and it's approximately 3 times 10 to the 8 meters per second. That's how fast photons travel in a vacuum, or light. You know, electromagnetic fields are made of what's called an ensemble of photons, a whole bunch of photons at one point that allows us to measure a value. And we could get into what a laser is and stuff. They're fascinating, the difference between laser and non-coherent propagation and stuff. But photons are the basic, they call them corpuscles of light. I've heard that said. They're the smallest known energy entity that makes up a light wave at any point in space-time. And there can be virtual and real photons. Now, my lecture time's over, but I'm just going to share one thing with you. One of the things that will help you learn astronomically faster than normal is becoming interested in the subject. I mean, when I had, what is one course used to drive me nuts? Chemistry. I had a course in chemistry that was huge amounts of memorization about processes and stuff, and I didn't see the reason why the process worked. I had no, if you don't understand why you're memorizing stuff, it doesn't really work. At least for me, it doesn't work. When I got into grad school and I had crystal chemistry and I saw that the guy named Linus Pauling wrote this book, got a Nobel Prize for this, the nature of the chemical bond and how electromagnetic energy and the minimization of it was the reason for all chemical reactions and chemical compounds. Then I understood that all that memorization was just telling me what the final result would be for the minimum energy stuff. All of a sudden, and I'm not going to go that way with you, I'm not going to try to give you a whole spiel on chemistry. I appreciated everything chemistry made sense. I understood what was going on. Back in the day when I took as an undergrad, especially low chem, it's just vast quantities of memorization. Do y'all remember the days of chemistry? With all those crazy reactions and stuff like that? You never knew why, they just said that's the way it is. Well, what I try to do is encourage people to get interested in the subject for a fundamental reason. So go and look if you have time. Go look on YouTube. That's something involving quantum electrodynamics or quantum computing, or really look at something related to electromagnetics to get yourself interested in studying propagation. Some of the neatest things that are going on in physics today. I love physics. What they're looking at has to do with information coming from vast distances, from things called black holes that are so far away, and they take a look at the effects of black holes on radiations from stars and stuff like this, and they are always talking about measuring things at great distances. They measure not only photons, or the optical stuff, but they measure gravitons. Has anybody here heard of gravitons? All right, well, gravitons, physicists have a way of coining terms that don't mean much to anybody, but they measure them in the same way you would an electromagnetic field. They have a very long antenna. It's just a solid rod about a mile or two long, where they look at the deflection of it. But what they're really working towards is the unified field theory, how gravity, how electromagnetic phenomena, the strong force and the weak force all interact, and what the coupling is. You know who Einstein is, I assume. Einstein, when he put down his general relativity theorem, he coupled gravity's influence on optical phenomena, the propagation of photons, and when they looked at the change in where stars should be, stars should be caused by the warping of the sun's gravity. Does anybody remember these things at all? Did you get this in physics? Well, that coupled a couple of these, but getting interested in the subject, and I wish I had something better prepared to tell you. If you can find a way to get interested in this stuff, it'll help you remember this stuff. I'm just telling you that. If you're just bored to tears with it, oh God, I'm gonna take it. It's gonna hurt. So, my office hours right after this class, and it's over. I'll get you a homework posted. Sorry. You need to see me.